Hello, a great welcome to this series on Plaxis. Myself Janajan P. This is tutorial number 9 and it will demonstrate the capacity calculations of a suction anchor using the Plaxis software. Now before taking you to the problem statement, let us first of all see what the suction anchors are all about. Basically, suction anchors are large cylindrical tubes open at the bottom and closed at the top and used for the mooring of different types of floating structures in the offshore petroleum industry, including exploratory vessels. They are also widely used in offshore wind energy industry. The aspect ratio L by T of suction pile is normally kept less than 10 and the thickness to diameter ratio is normally kept in the range of 0.3 to 0.6%. The installation of the suction pile is basically a two-step process, first involving its penetration under its own surface and thereafter by the application of the suction pressure within the pile. So let us first see the problem statement. So for the current tutorial, we'll consider a suction anchor with its diameter d equal to 5 meters and we shall consider an L by D ratio of 3. Accordingly, the length of the suction anchor will be taken as a 3 into 5, that's equal to 15 meters. And for the tutorial, we'll consider a pad location, that is set P equal to 7.5 meters. Please remember that pad is the location where the mooring tension will be transferred to the suction anchor, and the location of the pad requires multiple analysis so that we ensure that the maximum capacity of the anchor is mobilized with the translation as the main mode of its deformation behavior with a minimum rotation. And for the tutorial, we'll consider that the suction anchor is installed in a normally consolidated clay deposit of 30-meter depth. And regarding the soil parameters, we will use the Moore-Coulomb criteria to model the material. And considering that the capacity of the anchor are always mobilized for short-term loading, we'll use an undrained analysis for the tutorial. The unit weights of the soil will be taken as 15. So for the tutorial, we assume that both the stiffness modulus as well as the undrained strength, they vary linearly with the stiffness modulus equal to 100 kN per meter square at the surface and the undrained shear strength equal to 2 kN per meter square at the surface. And we assume that the increment for the tangent modulus or the stiffness modulus will be 500, and for the undrained shear strength, the increment will be 1.2. Both the phi as well as the dilatancy psi values will be taken as a 0 because we are considering an NC clay, and the interface coefficient, which model the interaction between the surface of the suction anchor and the surrounding soil, is taken as 0.65. Now for the pipe, we will consider a linear elastic material with the drainage type selected as non-porous, unit weight being taken as 78 kN per meter cube with a E-value of 2E8 kN per meter square. The Poisson's ratio will be 0.20 and the thickness of the suction anchor will be taken as a 0.03 meters, that's equal to 30 millimeters. So let us start the Plaxis. Okay, fine. So considering the circular cross-section of the suction anchor and the loading along the diametrical plane, we'll consider only one half of the suction anchor for the present tutorial as it will considerably reduce the computational time. So let us straight away start by filling the title. So we'll use a title of a suction pile analysis. So now let us start defining the model boundaries. So we'll have x max and x minimum as minus 25 plus 25, and here we'll use 15, so that's okay. So now let's start defining the stratigraphy using the borehole. So we'll create a borehole at the reference point 0, 0, 0. So let us start defining first of all the stratigraphy. So add a single layer with the top at 0 and the bottom at minus 30. Now let us start defining the property for the NC clay. So before that, let us set the head as 1 that is the water table will be above the suction anchor. So click the materials button and start defining the clay material. So let us call this as NC clay, and the material model will be more column. The drained type will use an undrained B-type analysis, and coming to the unit weight, will keep it as 15 kg per meter cube. Now let's start defining both the stiffness as well as the strength parameters, and the E value at the surface will be taken as 100 kg per meter square, Poisson's ratio 0.30, and we'll use the undrained shear strength at the surface as 2 kg per meter square. Now the advanced feature will let you define the increment of both the stiffness modulus as well as the undrained shear strength across the depth. So for the tutorial, we'll use an increment value for the E value as 500. And coming to the undrained shear strength, we'll use a value of increment equal to 1.2. So that's okay. So now let's start defining the interface coefficient, that is a capital R into value. So we'll use the manual and we'll set the value of R at 0.65. So that's okay for us. So thus we completed the definition of the NC clay. Now let's start assigning this material to the presently created rod. So just straight away go over here, select the NC clay. So press OK. So this completes our activities in the soil mode. Now let us proceed over to the structures mode in order to define the suction anchor, in order to define the soil plug inside the suction anchor, to apply the loads and the boundary conditions. So fine, so let us start first creating the top surface as well as the side surface of the suction anchor. So we shall proceed to create the anchor first by defining a polycurve. So let me first zoom this area. Okay, fine. So here I'm finding the grid setting. I will be able to snap only at 1 meters. So I want to snap a point at 2.5 meters. So this means that I have to reduce it to 2.5 meters. So go to options, visualization settings. Currently you will find that the grids are spaced at 1 meters. So I'll just increase the intervals to 2. That's okay. So let us snap a point that represents one edge of the anchor, that is at 2.50. So this is my 2.50. Just press enter. Okay, so let us start creating a segment. So the segment type will select as arc, and let us start the starting angle as 90 degrees. Radius, we know that is the diameter is 5 meters, so this will be 2.5 meters. And the segmental angle, we want to create a semicircle, so keep it as 180 degrees. And the discretization angle, we will keep it as the default, so that's okay for us. So you'll find that yes, a semicircular polycurve is now placed. Let us first start extruding this to the bottom of the anchor so that we'll be able to create the surface. So go to extrude. So first what you can do is you can just select this polycurve, which is essentially a semicircle. So go for the extrude function. So here we know that the length of our pile, the length of the suction anchor is 15 meters. So which means that we'll keep the z as minus 15, apply. So you'll find that yes, the pile surface is right now created. Now what we can do is we want to create a top surface also. So let us first close this polycurve. So select the polycurve and just click it. You'll find that there's an option called close. So once you have closed this polycurve, we'll be able to create a surface out of it. Again, right click on this closed polycurve. You can ask for creating a surface. Okay, fine. So we find that yes, now the two surfaces are created. One for the top surface of the suction anchor, and the other one is a side surface. Okay, so if you see the full view, you'll find that this is the entire side surface, and this is the top surface. Now, having done that, now what we can do is that we can start creating a soil plug version of the PLAXIS which I am using. It do not have the rigid body option to model the suction anchor. So what I will do is that I will create a soil plug inside this suction anchor, and then I will simulate it as a highly stiff elastic material. So let us proceed for that. So select the top surface. So it is already selected. Extrude it. So obviously we want to extrude it till the bottom. So -15. So apply. So this means that yes, we have created the soil plug that is inside the suction anchor, and we will model this as a stiff material. So having done this, what we can do is that we can start providing the properties for the top surface as well as the side surface. So before that, select the top surface, right click it, so create the plate. You can say that yes, the plate is created. Yes, this is the plate that is created. And now in a similar way, right click the side surface, and you can ask for create a plate. Okay, so that's also done. Now what we can do is we can start assigning the properties for these plates. So I have already defined the properties of the plate. So I have selected the set type as the plate. It is already defined over here. This is just to save the time. So let me just show you how it is defined. Please remember that this is a pile. It is defined in order to model the properties of the top as well as the side surfaces. And here you can see that the thickness is set to 0.03 meters, that is 30 millimeters. And the unit weight is a steel, so it's a 78 kilonewton per meter cube, and it is assumed to be a linear elastic or a linear elastic isotropic material with an E value of 2 E8 kilonewton per meter square and with a Poisson's ratio of 0.2. So that is how we have defined the pile material. Let us assign this pile material to the top as well as the side surface. Right click it, go to plate 1 and set the material, select the pile. Okay, so you can say that yes, the pile material is already assigned. In a similar way, let us assign the pile material to the side surface also. Right click it, go to the plate 2, set the material, select the pile. So we can say that yes, now the material is already assigned, the pile material is already assigned to the top as well as the side surface. Now we have already developed or generated a soil plug inside the suction anchor. We want to assign a stiff soil property to this. That property is also defined over here. You can see that soil and interfaces. I have also defined a property known as stiff soil. Let me just edit it and show you how it is done. And in this case, it is defined as a linear elastic material. And here I have assigned a property gamma, that's the unit weight as 15 kilonewton per meter cube. And if you go to the parameters, you'll find that here I have simulated a soil with a large stiffness, that is a 26 kilonewton per meter square with an associated Poisson's ratio of 0.30. So that must be good enough. So let us start assigning the property for this stiffer soil plug that is contained within the suction anchor. So if you select it, you will find that on the left side, the property, we have not assigned anything to it. So let me assign the stiff soil for it. So this means that the definition of the suction anchor is complete. Now what is left is we need to define the so-called an interface also. So let us proceed for that. So select, so here please remember for this suction anchor we assume that the failure mechanism is the one that involves a rigid body motion of this entire suction anchor. Accordingly, we assume that the slip take place only between the outside of the soil and the suction surface. And we assume that there will be no slip between the soil plug and the suction surfaces. This means that we need to create only one positive interface for this case. So what we can do is that we can just rotate it a little bit just for our convenience, and just select this surface and right click it and create a positive interface. Yes. So we find that the definition of the suction anchor along with the interface is complete now. We now need to assign a load also which acts as the pad eye position. So for doing that, what we can do is we can go straight away to the create point and here select a point load. So I will just select one point. So here I want to apply it at x is equal to 2.5. That corresponds to the outer edge of my suction anchor. And then y, I want to keep it at 0 because we are applying the load along the diametrical plane. And the z will be minus of 7.5. So as usual, you can see that PLAXIS has created a default unit load in the z direction. So let me just keep it as a, for example, instead of -1, +1, and fx also +1. So here you will find that yes, we have defined right now a unit load that is inclined at 45 degrees. So let me just use the front view, that will be much more clear. So this is my front view. Okay, fine. So you can see that right now we have applied a unit load, that is fx equal to 1 and fz equal to 1 kilonewton. That means our resultant load of square root of 2 kilonewton is applied at 45 degrees to the horizontal. So having done that, we are now ready to proceed to the mesh mode. So as you can see that in order to refine the mesh around the suction anchor, I have created a mesh refinement zone, and the length of this zone is 20 meters and the width is 5 meters, and it extends 5 meters below the bottom of the suction anchor. And this is to ensure that yes, we perform accurate calculation of the capacity of the suction anchor by refining the mesh sizes very near to the suction anchor. So this song can be easily created. What you need to do is that you have to first create 3 lines of the top surface, just extrude till the bottom surface, and then create an additional bottom surface. That's all. So now let us proceed over to the mesh. And in the mesh, we want to refine the region. So select this mesh refinement region. Currently, you can see that the fineness factor is 1. I want to reduce it to, say, instead of 1, the fineness factor of that 0.25. So go to the refine mesh option. Just go on, double click it till we get, say, 0.25. Yes, you can see that right now the fineness factor is 0.25. Thus ensuring that the elements in and around the suction anchor, they are finely meshed. So having done that, we can straight go for the meshing. Now for the balance portion, we will use an element distribution of medium, and that's okay for us. And start proceeding for creating the mesh. Meshing is complete. Let us preview the mesh. Okay, fine. So as you can see that we are using a final mesh size that is inside that mesh refinement zone, and for others we are using a coarse mesh. So this means the meshing activity is complete. We are ready to proceed to the staged construction. So now coming to the staged construction, I have defined basically the initial phase and 3 other phases, and let me just take you to a brief description of these phases. The initial phase, it is defined by default by PLAXIS. So if you double click it, we have used the phase procedure here. And in this phase, basically we calculate the stresses in the soil mass during the sulfate. And during this initial phase, ensure that only the soils are active, the place interfaces and the pointers are inactive. And now coming to the phase 1, that is a pipe installation. So if I just double click it, you can say that it's an phase that is corresponding to the pile installation, and it starts from the initial phase. Calculation type will be plastic, and we have kept all the numerical control parameters by default values. And during this pile installation, the pile loads will be kept inactive. Now coming to the phase 2, it represents a phase where the load applied at the pad I, it is a completely horizontal. That means it makes a zero angle with a horizontal. So if I double click it, you can say that this phase straight away start from the pile installation phase, and we'll keep the reset displacements to 0 in order to avoid the unwanted displacements in the systems to the sulfate. And all the numerical control parameters will be kept as default. We are not going to change anything over here. Now, during this phase 2, where the load is applied at 0 degrees with the horizontal, you'll find that the point loads are also kept activated. And here we have applied FX, that's a fully horizontal load 5000 kN, and the F set components are 0, so that the resultant force is 5000 kN, fully horizontal. So the final phase, that's a phase 3, is the one wherein we apply the load at the pad I, applied at 45 degrees with the horizontal. So if you double click it, you find that this phase starts from the pile installation, and we have for this the displacements to 0, and all the numerical control parameters are kept by default. And you'll find that here the point loads are also kept active, but they will have a different value. For example, we'll have an FX component which is nothing but 5000 into cos 45, and an offset component that is a 3535 kilonewton, which implies a resultant load of 5000 kilonewton that is applied at 45 degrees. So this means that we have completely defined the various phases required for the calculations. Now, having done that, we have to select a point for monitoring the calculations. And in this case, as you can see that we have already selected a point that corresponds to the center of the pile, that is 0, 0, 0, as the control point for monitoring the calculations. So now we are ready to perform the calculations. So press the calculate button and wait for the results. So as you can see, the analysis is complete. Let us start reviewing the results. So first, as usual, we will go for the stress distribution in the soil and rest on weight. So we have selected the initial phase, as you can see. Let us just quickly visualize the results. For example, let us see the Cartesian total stresses sigma z. Okay, so here you can find that yes, the stress distribution is already shown under self-weight, and the maximum value of the stress is 460 kN per meter square. This is something like against 450 computed by hand. So this is acceptable to us. So let us quickly go to the other important one, that is when the entire pullout is applied horizontally, that is the load angle at 0. And let us start visualizing the so-called deformations. And the deformations, we would like to see the total, for example, the deformations, let's say that in the z direction for a better visualization. So here as we can see that, so let me just zoom this portion. So here if you inspect this deformed pattern of the soil under a horizontal load of the suction anchor, you'll find that on one side we have got a positive displacement. There's a blue is a positive displacement, and on the other side we have got a negative displacement. That means this indicates that on one side, that means on this left side, we have got an active case getting developed for the suction caisson, and here on the right side we have got something like a bulging of the soil, and that means development of a passive region, just like the case of a behind a retaining wall. Now let's just see the flow pattern around this suction anchor. So I'll just like to, okay, you can say that if I just zoom it, you can say that here, yes, the soil particles are moving down on this side, and on this side, on the right side, you can see that it is moving up. So this is something like development of an active zone on this side and a passive zone on the right side of the suction anchor. So that's regarding the load angle, and here it is also possible for us to obtain a deformation profile. So let me just do quickly, let me just consider a cross section here. For example, I will consider say -30, a vertical cross section, and plus 30, and I want to consider that y equal to 0. That's okay. So okay, this is good enough for the correct visualization of the deformations. So let me just zoom this portion. Okay, fine. So here if you put the arrows, you can see that yes, the arrows here they are moving down, and here the arrows are moving up, and this is the bulging. So this is what we call as a caving on the left side, and there's a bulging on the right side. And if you want to quickly see how the soil deformation has taken place across this plane, you can just take a quick cross section. So I will just take a cross section across this. So you will find yes. So this is how the soil deformations have varied across this profile. We'll find that on the left side we find that there is a caving in, and on the right side we'll find that there's a bulging of the soil. So on this side we have got an active case, and on the right side we have got a passive case. So I think this is good enough for this case. Let us go to the next case, that is wherein we have applied the load at 45 degrees. So I'll just take a load case of 45 degrees. And again, I wish to see the how the deformation has taken place. So let me just take. Okay, this is good enough for me. So here, what you can say that it's just similar to here. Please remember that this is a case where the load is applied at 45 degrees. So again, on the left side, we find that there is a caving in. That means the soil moves as this suction angle is subjected to a 45 degree angle load. We find that there is a downward movement on the left side, and again here again there is an upward movement. And what is interesting to note here is that we find that the soil particles are also moving upward near the base. Look here, this is the, if I just enlarge this soil profile, you will find that the soil particles are also moving upward. So let us just zoom it. Yes, here you can see that the soil particles are moving upward, and here on this side you will find that it is moving downward. So this indicates that basically we are observing some kind of a reverse bearing capacity failure. So for the soil, when it is subjected to an inclined load. So that's all regarding the distribution of the deformations for the two cases. Now let us quickly proceed to how the curves, how the response of a selected point can be obtained under these two cases. So let us just select the curve point. Curve point we have already selected is a 0, 0, 0. And coming to the charts, let us go for a new chart. And let us proceed for selecting, for example, here I will select the project, and I would like to see the stage. So this is my M stage, and here I can select the corresponding point. Select the point, and here I would like to see the deformations. I would like to see the total displacements, for example U. So that's okay for me. So let me just select this and select only the whatever is required for this. I require only the load angle and the load 0. That's okay for me. Okay, now I would like to just exchange axis on the chart and just exchange axis. Okay, fine. So okay, definitely I will be transferring this data to the Excel, and I will show to you. And as you can see that it is first curve that corresponds to theta equal to 0 degree, and the second curve that is corresponding to theta equal to 45 degrees. So our observation here is that the pullout capacity of the suction angle is much higher at theta equal to 45 degrees, and it is the lowest one at theta equal to 0 degree. So let me just transfer this data to the Excel file, and I will show you the final computed pullout capacities based on the two scenarios, theta equal to 0 degrees and theta equal to 45 degrees. So finally, the data from PLAXIS, it is exported into Excel, and we have compiled a load displacement curve for the two cases. The curve in blue indicates the load application angle of 0 degrees, whereas that corresponds to the red indicates the load angle of 45 degrees. So you can see that at a theta equal to 0 degrees, the corresponding capacity is around 6,000 Newton, whereas for theta equal to 45 degrees, we find a very increased capacity of 10,000 kilonewton. So that is all for this tutorial. Thanks for watching.